All right, so we're gonna talk about the heat map today. So what is heat map? So what I'm saying about heat map is you have a domain and you have, let's say, call it D, and you had a heat function. So basically, heat is measured by temperature, so you can call it a temperature function. So it's a map on the domain D. So usually domain, I'll take it as a two-dimensional domain to a real number. Okay, so it's a heat function. And the heat map is a collection of contour lines of this function. Okay? So I want to connect the line, all the points which has the same temperature. So it's something like similar to you have a map which has contour lines on your map to indicate the height of your territory, right? So you want to see the same thing, how hot or how cold this part or that part is. So let's think about the simplest example of heat map. So let's say our D is, let's say we don't even have to have x-axis, but let's say this is y-axis and this x-axis, and this is when x equals to 1, and this is when x equals to 0. So your domain D is a strip, an infinite strip between these two vertical lines. I want to have a heat map. Well, let's suppose that our boundary have a certain temperature. So it's kind of a insulated. So it's preserved at certain temperature on this side and that side, and the temperature here is T equals to 0, and here is T equals to 1. So I want to see what's happening in between here. Well, there is a heat equation, but without thinking about heat equation yet, the easiest thing that you can think of about the heat map or temperature function in between these two boundaries is that the heat must continuously changes across these two boundaries. So it has to be temperature 0 and continuously changes to temperature 1 on this boundary. So you can think of this hxy, which is xy lies on this domain, to be equals to x, right? So when x equals to 0, then the temperature is 0. When x equals to 1, the temperature is 1. So you can guess that the heat distribution across these two boundaries inside of this domain is given by just formula x, right? So even though we have a variable y as an independent variable, input variable, it's not appeared here because you see there shouldn't be any changes across these vertical lines because it has to be the same temperature along the boundaries. So that must be the right one. And so let's talk about what is the governing equation to determine the heat map or heat function. So in the real life, the heat is flowing, right? So flowing means that it changes over time. So if you take the snapshot of your temperature at certain time, then it will have only the function of x and y. It only depends on where the position of the point is, but it really does not. The heat is changing. Your temperature at a certain point is changing over time. So the real equation of your heat function is a function in terms of x, y, and the time variable t. So heat equation is given by the following. So now we have to talk about the higher order derivative here, but let's think about this way first. So we have a change of heat over the time. So what does it mean? It's the change of heat at x, y at time t over time. So over time is the important concept. So you want to measure the change of your temperature over time at a fixed point. So this equation says this rate of change is governed by how fast the heat is flowing across the points. So we'll talk about this later in a deeper sense, and when we talk about line integral or surface integral. So this is the divergence of heat or temperature or heat energy, whatever you want to call it. So it means that the rate of change of heat that disperse at x, y at time t. So you want to measure how heat is changing fast across the point, not the time. Okay, so it's like you have a slope in a certain. If you're riding a slide, if the slope of the slide is steep, then you're moving faster, right? If your slope of your slide is not steep, very long but not steep, then you're moving slowly. So the rate of change of your heat or temperature is depending on how much the temperature between one point to another point to the next point is different. So if it's have a big difference, then the heat will flow faster. If it's small, then heat will flow slower. So over time, but you actually measure the heat change over time. So therefore, this is the heat equation that governs. It depends on the time, but you can also measure the rate of change over time by looking at the heat difference between 2 points. So this C is a constant that depends on your material. So if your material has high heat transference, so like a metal, then you have a higher C. But if it's not, then you have a smaller C. So it depends on material. Okay, but let's think about the general situation. So if heat is not constantly changing, in other words, if heat is not vibrating, right? Vibrating means that it's oscillating forever. If it's not vibrating, then at certain point, the heat map will be stabilized. That means there's no heat flow anymore. I mean, there's no changes of heat or temperature at certain point, even if the time is flowing. So eventually, you're gonna have equilibrium state of your heat map. So that means your heat function is independent to the variable T. So if the heat map is stabilized, i.e. the temperature at x, y is not changing over time, what happens? It basically means that your function h, which originally was a function of x, y, and t, is not a function of t anymore. So therefore, your partial derivative becomes 0, right? So h is not function of t anymore, right? So whenever you encounter equation, you have to be able to think of this equation in a physical sense. Let's say we have this equation. Don't think about this h as a kind of formula, but if I take the formula, take the partial derivative, it goes to 0. But think about the meaning. It means that there's no t. That means h has nothing to do with t. So h is not determined by t. So we can think of ignore the effect of the time, right? So h is now stabilized. So what does, in that case, the heat equation is h satisfies del h del x squared plus del h del y squared equals to 0, right? That now C doesn't matter anymore, right? So this equation, just this equation. So we want to go for this one. So we want to find the heat map or heat function h that satisfies this heat equation over a certain domain, okay? So let's talk about higher order derivative. So we have, I wrote this double, so second order partial derivative. So here's the definition. Can't see it, right? I think you have to change your seat. Can you see it? Maybe not. So maybe you can move, everyone can move a little bit. Can you see this one? Okay, so maybe you guys move this, move that to that seat. Higher order. Higher order partial derivative. So let's say h xy is our multivariable function, and which is real valued function. And when I say h over del x, del h, del x, it's a partial derivative, of course. When I say this, again, I'm just reviewing again because I want to repeat until you finally understand whatever or remember what it says. Best way to remember is the repetition. So we have computed this limit, right? But then I can do this for every x0 and y0, right? So you just give a number. So this is the number. So I want to say that this del h, del x is a function. So if h is a function, which is a map from certain domain to the real number, I can also say this is also a function that is defined on the same domain to a real number, where if I take x, y in this domain, then this maps to my partial differential at x, y. So this is now a function, two-variable function. So ignore that where it came from. Just think that's a two-variable function. We can think about the partial derivative of this function again. So partial derivative of, let's call it, let's say h1 here, h1 over hx. So we're doing the same thing. So when I take the partial differential at some point x0, y0, I'm taking the limit when x goes to x0, x minus x0, h1 of x, y0 minus h1 x0, y0, right? So what am I doing here is I'm taking a value of h1, but what is h1? h1 is the partial derivative. So what I'm actually doing here is taking a partial derivative of h at point x, y0, and I do the same thing for here, and then take these things into the limit. So since I fixed my x0 and y0, this could be just a number, but this one could be a value or formula in terms of x. And then we can compute the limit to find this. And this is also value. It's called the second order partial derivative. And we usually write this way. So this is taking a partial derivative of partial derivative at x0, y0. And by abbreviating this curly d, so this del, it's called the del, and it's actually d, come from d, can be considered as a symbol that you can multiply with. So it's kind of, it's a funny thing that you can multiply the symbols, but the abbreviation notation is you put del square h on top and del x square. So here the del is the separate thing, and this del x is the one thing. You cannot separate out del and x here. So this is just the notation of this definition. And this is called second order partial differential. Okay. So going back to the first, so this is called first order partial differential. And there is another partial differential, right? So first order partial differential, there are two, because this h is two variable function. And how many second order partial differential are there? But this, two? But you can take this one either x or y, and also you can take this one as x or y. So how many combinations do you have? 4, yes. There are 4 second order partial differentials. But here is the theorem. So technically, these 4 partial differentials are conceptually different, but when you actually compute values, some of them are actually turn out to be the same. So let me just write the notation and then introduce the theorem. So notation is this h del x del y. So if you have different variable to take the partial differential with, then which means this means that you're taking, so preserve the order. Think about, you have to preserve the order. So what this means is that you take the partial derivative of h by y first, and then you take the partial derivative of this in terms of x again. Okay? So if, let's say, t is a function of 3 variable, then you can have a third order partial derivative. So in that case, we write it as del x, del y, del z. Or you can have other partial, higher or third order partial derivative. But in this case, what happens is you take, so this is a partial derivative of, in terms of x, of the second order partial derivative, del y, del z. And this is partial derivative of, in terms of y, of the partial derivative in terms of z. So always think about the order. And also, if you think about this as del x, del y, del x, then even if you have a 2 del x, you cannot switch the order. So basically it means that if you take the partial derivative in that order, you first take the partial derivative of x and y and then x. Okay, that's the notation. And these are these are partial differentials, which means it's a number. But when we say without mentioning the specific points, it means it's a function. Usually it means function. So when you plug in the number, plug in the coefficient of numbers, point, then we get the partial differential as a number. So that's the function. You plug in the point, so you get the number. Now, here's the theorem. So theorem. So in the two-dimensional, two-variable case, if this second-order partial derivative and this second-order partial derivative are continuous function, then these are the same thing. So there's a rigorous statement about more rigorous way to state this theorem, which is if these two second-order partial derivatives are continuous at a certain point, then this value, which is the partial differential at that point, are the same, but just making it a bit more general state. So if you have these two functions, which are, again, two variable functions, are continuous, then the values of this function must be the same at every point, which means that they are the same function. So mostly we're talking about this type of situations. So whenever you have partial differentials, in this case, so in that case, you may think this as kind of thing that like del x squared, del xy. So you can just interchange the order of partial differentials freely if you know that this third order partial differentials are always continuous. Okay, so going back to our heat equation, what does this say? So we have two higher order differential or derivative. So these are second order derivative of h, just two of them. I mean, there are basically four of them, but we just took two. And they are not zero functions, but somehow if you add them together, it must be zero functions everywhere. That's what this heat equation says. Okay? So what kind of function satisfies this equation? So think about the example that we saw before. So if h, x comma y equals to x, does it satisfy this equation? So what is first order partial differentials? What is del h, del x? 1. And what is del h, del y? 0, yes. And now what is second order derivative? Del x? 0 and y? Also 0, yeah, because it's 0. So in this case, these are both 0. So therefore, you add to 0, right? So this satisfies this heat equation. So therefore, we can say this is our heat map in our example situation. And let me define one more thing, so because it's going to be important later. So definition. So any function, let's say two-variable function satisfies this is called harmonic function. So what is this notation? Because I just want to introduce notation. So this notation is del square del x square plus del square del y square h. So basically, we call this kind of thing as an operator. So operator means that it's acting on some function. And nabla square is defined to be this operator. So it's an addition of two operators. Each of them is a second order partial differential. And when you put this symbol onto h, then it gives you partial derivative. Okay, so whenever the function satisfies this equation, or same as this one equation, equals to 0, then we call this a harmonic function. And this also connects with the remark, the symbol, this triangle symbol. So this symbol is called nabla, and this symbol is called Laplacian. And we're going to talk about this later, but nabla is defined to be a symbolic vector, which is given by operators. So if you apply nabla into two-variable function, then it's a two-dimensional vector. It's kind of a symbolic vector because the entry of the vector is not number, it's operator. And when you say nabla square, which is a Laplacian, it kind of means that you're taking an inner product between the nabla itself, so that you're taking inner product with itself, so that you're kind of multiplying the squaring and then adding together, right? So you're applying. So when you say it's a multiplication, since it's an operator, it's not really a multiplication because it's not a number, but it's a successive action of the operator. So you're applying the one operator and then another operator again. So we're going to talk about this a little bit later. So and then this y is successive operator. So when you apply this to, it's kind of same thing as second order partial differential operator, right? You apply del x onto function and then apply another del x partial derivative onto that function again. So it's kind of second partial derivative with x, and same for y and y. So you get this, right? Second order partial differential operator. All right, so that's the background of the heat equation. Now let's think more about harmonic function. So in physics, you probably have seen this kind of thing, maybe last semester or maybe not. So let's talk about Laplacian and in terms of polar coordinates. So what is a polar coordinate? It's describing your point in terms of r theta instead of xy. So r theta, I think we talked about this a long time ago. Not that long time ago, but at some point. So r is the distance between the point and the origin, and theta is the angle between the line joining the origin to the point with the x-axis. So when we have r theta, we can convert it into xy, right? xy, where x is r cosine theta and y is r sine theta with this picture. So we have x comma y right here. Then you can find the angle and the radius, the distance. And your x coordinate and y coordinate is r cosine theta and r sine theta, right? So let's call this map as T. So we call this kind of map transformation because it transformed the polar system to Cartesian system. And then let's try to take the derivative. Okay, so let's say we are taking derivative at certain r and zeta. Let's call it r naught and zeta naught, r0, zeta 0. So remember, I'm telling you new thing and also reviewing things that we have learned before. What is the derivative? It's a matrix. What's the size of a matrix? What's the number of the row? How many rows are there? So it's a 2 to 2 functions. How many rows? 2, yes. Columns? Yes, 2, 2. The 2 by 2 function. So what's the first entry here? One row, first column entry. So each row, it has the same output function, right? So first output is x. So, and then each column is about partial derivative in terms of the input variables. So first one is about what? X, partial derivative of x by what? Yeah, f is x here, the first function. And you take the partial derivative with which variable here? Well, this is the first column. So then you have to go for the first element, first variable. What is it? R, right? And you're taking partial derivative at this point, right? So you have R0, zeta 0. And what about the second? What is it? Yes. And this was del y, del r, and del y, del zeta. Okay, now let's compute this. What is this? X is r cosine zeta. When you take the partial derivative, I mean, definition is using limit, but you can consider it, you can do it with a trick by considering other variable as constant. So consider zeta as a constant. You just take the derivative of r cosine zeta. What is it? Cosine zeta, right? But now we want to put the differential, not derivative. So it's cosine zeta 0, right? And how about the second column? Minus r sine zeta, right? This one is sine zeta 0, r cosine zeta 0, right? So what does that mean? So it has something to do with the mapping in between r theta plane and xy plane, right? So let me draw it here. So what we said before is to understand how to understand these entries of the derivative. So here we have r zeta, and the transformation maps r zeta to xy. We are starting with certain r and certain zeta. Of course, I'm kind of assuming r as a positive number and zeta in between 0 and 2 pi, but it can be any number in principle. And you know it's going to x0 and y0, where x0 is r0 cosine zeta 0 and y0 as r0 sine zeta 0. And this derivative gives differential gives the instant movement of the output space according to the input space, right? So what happens when I move along this r direction? So what did we say about this direction? So it's about del r, right? So if you're moving in the unit length or unit speed along r direction, you can call this del r, okay? As a symbolic notation of vector. So del r is 1, 0 vector at certain point, r0 zeta 0, and it's changing the r value from r0 in the speed of 1. And what happens when you move your point instantly into this vector? You are changing your x comma y, or x0 comma y0 in certain direction. And that direction is governed by matrix multiplication of differential and the vector 1, 0. So this is cosine theta 0 minus r sine theta 0 sine theta 0 r cosine theta 0 times 1, 0 is what? Do the matrix multiplication. You get first column, right? First row is cosine theta, second row is sine theta. And now you can convert this into two-dimensional vector. So this vector is a vector at x0, y0, which means that it's a vector that represents the movement of a point x0 and y0 as the point r0 theta 0 is moving in this direction on this xy plane. So it means that it's moving in the speed of cosine theta 0 in x direction and moving in with the speed of sine theta 0 in y direction, right? So this can be written as cosine theta 0 del del x 0 plus sine theta 0 del del y 0. You have to follow me carefully, and if you don't understand, then you have to ask a question. Again, I'm using the partial differential symbol as a vector to represent certain direction. So here, del del x represents the horizontal direction of the unit speed, and del del y with the vertical direction with the unit speed, plus 1 speed. So it's moving upward. So whenever you want to say the movement of a vector with the coefficient a and b here, then you just multiply that a and b to the vector, unit vector, in the corresponding direction. So this is your movement. So here is your movement, cosine theta 0 del del x plus sine theta 0 del del y. So what did I say when you think about this situation with the symbol like this? You want to identify these two things as the same thing, because in fact, what we are doing here in these two different spaces is nothing but changing the perspective of the point. So it doesn't matter whether you move your point in r theta space or xy space, because eventually we're going to do something on these spaces to get some value or some movement in a three-dimensional space, like a robot arm or whatever. Therefore, you can consider this equals to del del r. That's the same thing. Okay? And how about when you move along this direction, del del theta? So del del theta is same as 0, 1 direction, right? So instead of having 1, 0, you can put 0, 1 to find out the coordinates. And in that case, this is going to be the vector. So del del theta is now what? These two are the coefficient, right? So minus r sine theta del del x plus r cosine the theta 0 here, theta 0 del del y, right? Okay, so now we can actually drop the 0 here. So it doesn't matter whether we see specific value here, because it will work at every point. So let's just drop the 0 notation here. So everything is just looks like formula here. So 0 is not required. You're not going to put the number here. Just everything is just a variable. Everything works the same way, whichever point we look. Okay, so here we have this. So now what does it mean? So it means that if I move my point here in r direction, then in xy plane, I'm moving farther away from the origin with the same angle. So if you think about the circle centered at the origin of the radius r, then when you change your r direction, you change your r in the r direction, you're moving away directly from the origin, right? So that's where you get this. And when you want to represent that direction in terms of xy coordinate, that's the coefficient you need, cosine theta and sine theta. What's the norm of this vector? 1. When you have cosine sine, you're always 1. You're moving in the speed of 1. Now, think about the other direction. When you move your theta in theta direction, then you're changing your angle without changing your radius. So you're actually moving along this circular rim. And now, it's kind of angular velocity. You're changing your angular velocity. But in xy plane, if you change your angular velocity, the actual velocity moving along this circle depends on your radius. So think about your angle is changing in 1 radian per second. If your radius is 1, then you're moving in 1 meter per second, one unit of vector, the velocity. But if your radius is 2, then you're twice faster, moving twice much faster than when the radius is 1. So you need the factor r. And the direction is actually perpendicular to this direction here that we found previously. So you can see that if you take the inner product, you always get 0. So these two are description of your vectors in r theta plane. But what is really interesting is that even though we use this symbol as a symbol for vector, we can also use it for symbol for partial differentials or partial derivative, just as we did for this kind of notation. So let's see what's happening here. So don't forget, we are doing this for representing the Laplacian in polar coordinates. So eventually we're going back to the Laplacian, but here, let me write that out this again. So del del r equals to cosine theta del del x plus sine theta del del y, and del del theta equals to minus r sine theta del del x plus r cosine theta del del y. So now, let's try to solve it for del del x and del del y. So this is an expression where del del r and del del theta in terms of del del x, del del y. Let's reverse this. So what is del del x and what is del del y? Well, first of all, let's try to find del del x. We need to get rid of del del y. So let's multiply this part with r minus r cosine theta, and this part with sine theta. So everything on the left and right. And then let's add them together to get rid of this part, right? And then this cancels out. So in that case, what we have is what? Minus r cosine square. And this one is, I think it's better to put minus here. It doesn't matter, right? So if I multiply r cosine theta, this becomes r cosine square. And this becomes r sine square. So when you add them together, you get this r, right, as a coefficient of del del x. And you get the coefficient exactly same as that. So we have r times del del x equals to r cosine theta del del r minus sine theta del del x, del del theta, right? So instead of writing del del r, so it's saying that if you move your point in xy in x direction, then it tells you how much your r and theta changes instantly. So it changes this much. The r direction changes r cosine theta, and theta direction changes minus sine theta. So anyway, so we want r to be get rid of because this is what we want. So this is sine over r, okay? And to get rid of y, to get y, you have to get rid of x. So therefore, let's try to multiply r sine theta above and cosine theta above and add them together. So you get sine theta del del r plus cosine theta over r del del theta. So basically what I did is actually finding the inverse matrix of this 2 by 2 matrix, if you know what inverse matrix is. But anyway, so now what we want, as I said, is to look at these two vectors as a partial differential operator. So I want to find out what this second order partial differentials is. So as I said, this is applying del del x on del del x, right? Right? Applying del del x to del del x. And I know that del del x is this. So it's del del x cosine theta del del r minus sine theta r del del theta. So any questions? You have questions? Yeah. What's the question?
Like how get the divided the del x from like right to vector f?
Divide this one?
How get those equations from the upper ones?
Okay, so let's look on the second one because I did the second one. So we have we want to survive. We want to leave del del y but delete del del x. So I want to make the same constant coefficient for del del x here, but the difference in sign. So I multiply r sine theta and cosine theta to get the same coefficient but different sign. So when I add them together side by side, I get rid of del del x, right? So in the right hand, so in this part becomes r sine square plus r cosine square, so you get r, right? The coefficient for del del y is r, and the coefficient for del del r is r sine theta, and this one is cosine theta. So in principle, r times del del y is equals to r sine theta, that r sine theta del del r, plus cosine theta times del del theta.
So we multiplied, for example, x cosine to, we multiplied the whole second equation to x cosine theta, or what?
No, just divide r on both sides.
That,
Yes, to get del del y equals something. Because there was r. It's just the same, it's solving system of linear equation. You know how to solve it, this system of the equations, linear equations, to get rid of other variables. So consider these are just variables. Mm. So you can try by yourself if you want to later. The important thing is we have the expression of this in terms of the others. It actually came from our initial equations. Okay.
yeah,
Yeah. Okay. All right. So let's try to think about this. So this is one of the sum end in our Laplacian, and I want to express this in terms of del del r and del del theta. So the meaning of this is applying same operator twice. So the same as this operator this operator acting on this operator, and this operator is same as this in terms of del del r and del del theta. And now what I need to do is applying operator del del x on this operator and that operator and add them together. But this one is also not in terms of theta and r, so I need to change this into cosine theta del del r minus sine theta r del del theta, and apply to the same thing here. So now I can separate out this part and that part and applying to these operators again. So let me show you how to do this. So first of all, what happens when I apply del del r to del del x, which is this? Cosine theta del del r minus sine theta r del del theta. And let's carry out computation. So this one is just there without we don't have to do anything here. The cosine theta is just coefficient. So cosine theta, and now I want to apply del del r to here, to cosine theta del del r. And then I want to apply this to here. So it's cosine theta del del r applying to sine theta over r del del theta. Okay, now think about this one first. I have some function n multiplied with the operator. So it's like a product rule. If you have a product of two functions and you want to take a derivative, you have to take the first derivative of the first factor and then add the derivative of the second factor. Same thing, because the partial derivative in principle is the same as the normal single variable derivative because it considers all the other variables as a constant, right? So cosine theta, take the derivative of cosine theta in terms of r. What is it? 0. So we don't have to worry about this. 0, but let's just leave 0. And then you apply this into the second factor here, not here because we already did here, this part. So cosine theta survives, but then now you're applying this del del r twice, you get the second order partial derivative operator. Okay, then how about this? So now cosine theta is still here. You want to apply this to here and first, and then here. So when you apply this first, sine theta is constant, so just leave it as constant. So it's 1 over r that you're taking partial derivative with, r. So it's minus r squared, and sine theta. And don't forget this, when you do the product rule, you don't just get rid of the second factor, right? So this del del theta is here. It's not disappearing. And then you apply second sum as applying this one. So you get the same coefficient here, sine zeta over r. But then now you have second order partial derivative. First, take the partial derivative in zeta, and then r. So square there r, there zeta. Okay. So let's simplify this a little bit. So we have cosine square theta, there square, there r. And we have sine theta, cosine theta, r square, there theta. And minus sine theta, cosine theta, r, there square, there r, there theta. I think I forgot one more thing here. No? Maybe not. Anyway. Okay. We have yeah, I think I forgot one thing. What did I forget? Oh yeah. This is just one of this, right? I only did this part, so I need to do this, right? So I only applied this operator to here. I need to think about this operator. So let's do the computation. So we have minus sine theta over r, there theta, to cosine theta, there r, minus sine theta over r, there theta. Okay. So now I know that you're not ready, but let's do it computation a little bit faster. So again, I can apply this here and here. So when I apply the operator on the first factor, I get minus sine, right? So get sine square zeta over r, and there r. And then if I apply it to the next, you get minus sine theta, cosine theta over r, second partial differential operator. So we have there r. And then apply this to here. First here, we get minus cosine theta. So it's sine theta, cosine theta, r square, there theta. And then to here, we get plus sine square theta over r square, there square, there theta square. So you have to add these thing here and these thing together to get del x square. Okay, del x square in terms of polar coordinate is having these operators, applying the partial differential operator on the function. Okay, so I'm not going to do the del y, but give you the answer and then see what happens when you add these two together. So let's write it here. So when you do the similar computation, I urge you to do this. You have to do it by yourself once in your life because it's really important. So it's going to be the sine square, there r, minus sine theta, cosine theta, r square, there theta, and sine theta, cosine theta over r, there theta, and what? Cosine square theta, r, there r, plus sine theta, cosine theta, r square, minus sine theta, cosine theta over r square, there theta. Let's erase a little bit here. And also I want to make sure that it's not confusing to anyone, so we can erase everything except for the result. Yeah, so I can erase this part, right? So I can erase this part. So this is their x square. Okay, so that's their y square, and I think I need one more. Cosine square theta r square, their x square. All right, so now I expressed my del x square and their y square. Let's add them together because I want to know how can Laplacian expressed in polar coordinates. So imagine we can add them together, their x square and their y square. There's some canceling and there's some the merging. So this one and this one are the same thing. So sine square plus cosine square is 1. So we get their r square. So let's cross out when we used it. So and then the next one, this part and this part have the same but different sign, so we can just cancel this out. And how about this one? Also canceled out. This one and this one cancel out. And how about this one? So now we have cosine square, sine square, which is 1. So we get 1 over r, there r, right? So we use this, so cancel, cross out. So in this one, and this one also cancels out. And this one also cancels out. And now this one and this one will become 1. So it's plus 1 plus r square, there theta square. So this is the expression Laplacian in polar coordinate. So why am I doing this? Because I want to figure out some kind of harmonic function in a different system. Not in xy coordinate, but in r theta coordinate. So let's say I have a function h in terms of r theta, which is log r. Is this harmonic function? So as I said, it doesn't matter whether I express my function in terms of r theta or xy, because I'm talking about the same space. It's just different perspective. So if I had to write this function in terms of xy, it has to be log of x squared plus y squared square root, right? And of course, because of this definition, r is not 0, which means that xy cannot be the origin, but that's excluded from the domain. But you can do both ways. You can either to show whether this h is Laplacian by applying the Laplacian xy coordinate to this function, or you can apply this formula to this function to say it's a harmonic function. So let's try both ways. Let's try both ways for now, and then I'll show you another example without applying the xy coordinates. So first of all, look at this one, xy function. So I'm saying again, I'm looking at the same function but different expression. Okay. So del x h, what is it? So first I have to take the first order partial derivative of this function in terms of x. So I get square root x squared plus y squared, and then so that's the derivative of log, and then take the derivative of the inside, which is 1 over 2 1 over square root of x squared plus y squared, and then 2x, right? Take the derivative of inside square root of x squared plus y squared, you get this. And 2 cancels out, and then this comes, just make it clean, you get x squared plus y squared x, right? And then you take the partial derivative again, because that's the one operator of the Laplacian. So, and then you get x squared plus y squared squared. I'm assuming that you know how to take the derivative of a rational function, right? So consider y as a constant. So what happens is you get x squared plus y squared minus x times 2x. So you get what? Minus x squared plus y squared and x squared plus y squared squared. That's your second order partial derivative in terms of x. And you can imagine what will happen when you take the partial derivative in terms of y, because it's symmetric. So you can just switch the role of x and y. So it will be x squared minus y squared, x squared plus y squared squared. So what happens when you add these together? It becomes 0, right? So you know that the Laplacian is 0 on this function. So you know that this is harmonic function. This is harmonic. We're looking for harmonic because we want the hit function, because the hit function must be harmonic by definition. But then also you can apply the Laplacian with the polar coordinates onto the polar expression of the function, log r. So this one is kind of complicated, so maybe this one will give you an easier way to check the harmonic function. So think about you plug in these operators and add them together and to applying this function. So what is the second order derivative of log r? So we have del r of log r, and this is del r of 1 over r, and it's minus r squared. That's one thing. And let's do it again. So with the different 1 over r, del r applying log r is 1 over r times 1 over r, which is 1 over r squared. Okay. So what about this one? So we get 1 over r squared. There theta square on log r, but R is constant when you take the partial derivative in terms of theta, so it's 0, right? So you add this together, it's all three together, you get canceling out, right? So you know that the Laplacian is also 0 on this polar expression log R. So we know that H is a heat map or heat function. It could be a heat function if the domain is right. And there's another example. Let's say R theta is just theta. H is a theta function. Okay, so how does theta function is defined? So if you want to express a theta function, it depends on where your range of theta is. But let's say theta is from 0 to pi. And if you want to express this function theta in terms of xy, where the range is from 0 to theta, you can use arc cosine, the inverse cosine. So this is cosine inverse of x squared plus y squared of x, because that gives you the theta in between 0 and theta. So now it gets really complicated. If you want to use this formula to find out whether this is harmonic function, because now it has an arc cosine and taking a derivative many times, and also if there is a rational inside. But let's think about this polar expression. Just by looking at this and the Laplacian, what will be the Laplacian of H? So now you plug in theta and apply this operator on theta here. So the operator del del R will make it 0 because theta is considered constant, right? Then also the operator, last operator, is the second order operator, second order partial derivative. But this is the first order degree polynomial. So when you take the partial derivative twice, you get 0. So you know that H is also harmonic, right? So there is reason why I'm mentioning these two functions, because these are the basic functions that we're going to use to find the heat map. But this also covers some important fact about the partial derivatives and meaning. So everyone okay with this? Ask a question if I give you some minutes to think of, and ask questions if you have any. You have to be able to, you don't have to understand all the computation, but you have to be 100% sure what we are talking about. Do you have a question? No questions? Yes.
Function is like harmonic in Cartesian, does that mean it's also in harmonic in polar?
Yes, yeah. Because we don't separate out the harmonic Cartesian coordinate with the polar coordinate. So once you have a polar coordinate, we're talking about the Cartesian coordinate corresponding point, right? So we're always talking about one space, one plane, right? Only different by the perspective, how we recognize that point, either polar coordinates or Cartesian coordinates. All right, so I was hoping that I can give you a coding example, but let's probably have not that. Let's postpone it next time. So I want to finish the background, theoretical backgrounds to do the project 5. So about the heat map, drawing the heat map. Okay, so here is the situation. Let's consider there is an upper half plane. So which means that our space is not the entire plane, xy plane. It's only the upper part of this plane. The y goes to 0. And you can also include the 0 part. And what I want is, let's say this is my domain. So I consider this as my domain of heat flow or heat map. And this is 0. And let's say this boundary. So it has boundary, which is x-axis, but I want to separate this two boundary in two pieces. The right piece has temperature C1, and on the left piece has temperature C0. So when I say the temperature is C0 and C1, it means that it is somehow preserved at that temperature with a flow of heat or flowing out of heat. Okay, so it's not thermostatic. I mean, it's somehow it's not insulated. Somehow the heat is flowing out and flowing in. But all I want is just to have a stable heat on the boundary. Now that's my only concern. I have a boundary condition on this boundary of the domain. I want to know what's going on inside. So all the information I know, all I can do actually on this domain is what I can do on the boundary. I can insulate the boundary, but I don't know, I have no control on the inside. The inside is flowing, the heat is flowing by the law of heat equation. So what's going on? What's going to be the heat map? So what's the formula of my function h? So all I can do is find the harmonic function because that's what I want. The heat equation gives me the only condition that heat function must be a harmonic function. So I need to find a harmonic function that satisfies the boundary condition that when you have y equals to 0 and x negative, the value is C0 and value of C1 in the opposite. So this must be theta. No, theta is not theta. So this must be C1 plus pi C0 minus C1 theta. So considering the theta is from 0 to pi, okay? Why is this equation, why is this formula harmonic? Because it's a first order degree polynomial, right? So this is our constant, C0, C1 are just constant, pi is constant. It's just degree 1 polynomial, and if you have a degree 1 polynomial applying the Laplacian, you know that it's 0, right? So why does it satisfy the boundary condition? Because if you have a point on the boundary on the right-hand side, your theta is 0, right? So your theta is 0, so you get C1 on the boundary, right? And on the other boundary, your theta is pi. So here theta is 0, and here you have theta pi. Of course, there are some other angles in between here, but I'm not care about this. I only care about whether the function's formula satisfies our boundary condition. When theta is pi, it must be C0, and theta is pi, that means you have canceling a C1 here and only C0 survive. So therefore, I know that this function satisfies the boundary condition and it is a harmonic function. And that is enough to say that this is the heat map. This is the function that describes the entire heat function or heat or temperature inside this domain D, upper plane. And let's try to consider this in terms of x and y. So I said this in r theta, but as I said, is h. If I write it in x and y, all I need to do is change this formula of theta in terms of x and y. So this is C1 plus pi over C0, C1, cosine inverse square root x squared, y squared over x. That's my function. Okay. But I don't have to go for the harmonic function anymore because I already showed it. Okay, so that's one situation. That's one situation I can think of. Let's make it more complicated. So how about, so here, this is x equals to 1, and this is x equals to 0. And how about I change the boundary, the cut of the boundary into different place? So here I cut it into the center, but now let's move our cut a little bit to the right. So we have C0 temperature on the right side after x equals to 1 and C0 on the left-hand side. So in this case, if I want this boundary condition, what will be my r theta to be? So it's the same thing, but your description of theta must be shifted to the right by 1, right? So originally, the theta is a function of x and y, even though you want to admit it, because if you can always consider this as a function of x and y. So if you want to consider in x and y coordinate, this must be a shifting of the function to the right by 1, So therefore, x must be replaced by x minus 1, comma 1, comma y. So this is your function. So what does that mean? So if you think about the point x, comma y here, then you're measuring angle here. So this theta is measuring this angle. This theta is measuring angle from origin. So there's a difference, right? So I want to measure the angle between this point and the not origin at 1 and see if the angle is 0 or pi. So if it's 0, I want C1, and it's pi, then I want C0. That's what exactly this equation says. So if I want to represent into xy formula, then this is C1 plus C0 minus C1 over pi of cosine inverse. The same thing, formula. The formula is same thing, except that you have x minus 1 instead of x. Okay? So now let's make it a little bit more complicated. So we only have 2 temperature and 2 pieces of boundary. Let's make it more boundaries. What if I have 4 pieces of boundary at x equals to 0, x equals to 1, and x equals to minus 1? And let's say this is C0, this is C1, the temperature is C1, and this is C2, and this is C3. I still want the heat map on the upper plane. I don't care about the down below. I just want H to be expressed in terms of R theta because it all depends on the theta. So I'll give you the answer and think by yourself why does it make sense. So I'm just trying to generalize the pattern here. So we have C3 plus C2 minus C3 over pi theta x minus 1 comma y. I'm going to make it into one big line here. So we have C1 minus C2 over pi theta x comma y. And plus C0 minus C1 over pi theta x plus 1 comma y. So actually it's a function of xy, not r theta, because I already mentioned xy. So it's a function of xy here. So think about this one by one. Suppose that I am at the point xy lying on the rightmost boundary piece. So then what's the value of this function? Let's make a A point, B point, C point, D point. Okay, so at A, theta x minus 1 y, maybe make a table here, theta x y, and theta x plus 1 y. So the value of these functions at A is what? This one is 0, yes. How about this? Okay, so this one tries to measure the angle where the origin is 0. So this one is trying to measure the angle as if the origin is at 1, right? The same way I did here. So A point is still at the angle 0, even if I move the origin here, right? Yeah, so 0, 0, 0. How about B? So what's the angle at this? What's the angle here? What's the value? So this function measures the angle as if the origin is here. B is at pi degree because this is the origin. We're measuring origin here, pi, right? Pi. Yeah, how about this? So measuring angle as if the origin is here. Yes, 0 and 0. How about C? What's these numbers? So you're looking at C in terms of origin is here, so it's going to be pi, and if the origin is here, it's still pi, but if the origin is here, its angle is set 0, right? How about D? All is pi, yes. So eventually, if you have these theta values, what's the value of H? So at A, everything is 0, 0, 0, 0. You got C3, right? So C3 here. When it's pi 0, 0, this is 0. C3 minus C3, it's C2, right? So at C, pi, pi, 0. So you get C3 cancels out, C2 cancels out, you get C1, right? And then D, C0. So we get these. Now we have the boundary condition. Okay. Now, is this Laplacian? I mean, is this harmonic? Yes. Why? Well, first of all, this is harmonic function. I know that, right? And then these two functions. So this is also harmonic because it's a constant function. Always constant function is 0 when you take the partial derivative. So the problem is these two functions. I need to ask whether these two functions are harmonic function. Actually, I had to ask this question at here, but let's do it here. So why is these functions harmonic functions? So it's a shifting of a harmonic function right here, right? So the question is, if you have a function defined on a plane or a domain, and if you make another function by shifting the value of function, not shifting the value, but shifting the entire domain, and you get another function, is that function still harmonic function? Why?
Even if we shift input, we get the same output.
Yeah, basically,
Not the same input, the same shifted output.
yeah. Yeah, kind of, I mean, basically that's the reason. But so if you think about this concept intuitively, sometimes it gets really clear. I mean, it's a kind of obvious thing. So if, let's say, f of x is harmonic on, let's say, r squared, r2, then if I take a shifting in xy direction, okay, then it's harmonic too. Because what is the meaning of harmonic here? It means that if I take these second order partial derivatives at any point, let's say x0, y0, it must be 0, no matter what point I'm putting in, right? So what do you mean by shifting? I'm shifting, instead of x0, looking at x0, y0, I'm looking at x0 plus a, y0 plus b. I'm looking at the partial differentials of the function with the second order at shifted point. But what does the condition says? It's harmonic on every point. So if the sum was 0 here, it has to be 0 even if you're looking at different point, because the condition says it's 0 here, 0 there. Everywhere it's 0, right? It doesn't matter, you change your point, right? So in this case, we're not shifting in y direction, but if you're shifting in x direction, you're only looking at the off-plot plane, you're having the same domain. So what's the difference looking at the partial differentials sum to 0 here and there? It's the same thing. It's always 0, right? So we know that this is also harmonic functions. So it's a sum of harmonic function. Therefore, the entire function is harmonic. So it must be the hit function. So so far, we found hit functions that satisfies this boundary condition. So now we can put any value for C0 to C3. It could be negative or positive because the temperature could be negative. But anyway, what happens, we will see in the contour lines of this function is that, so it's not going to be like always something like maybe something like this, or maybe this, you see, something like this. The contour line will appear naturally once you have the function without knowing that how the points are the same, how the temperatures at each different points are the same. if you know how to draw the contour line of a function, then the contour line naturally shows which points are having the same temperature and how this contour line gives you the equal temperature points and equal kind of a contour lines, so we can get the idea of where is hotter point and where is the colder point. That's the whole idea about this heat map. And in the book and also in the project, I wanted to do something more because this kind of gives you, maybe this is the domain that you want to work on. You have a large plate that has transferring the heat, and you want to insulate the boundary of a plate and then see how the heat are distributed inside of the plate. But sometimes the plate has a boundary, but this one has no boundary. So once you have that situation, you can think about a different shape of the domain. And one of the shape we can think of easily is the disk. So what happens when I have a metal disk and try to set the boundary temperature of each quadrant of the boundary into different temperature? So let's say this is C0, C1, C2, C3. So there are 4 pieces of this boundary, and what I have to find, in order to find the heat map inside of the disk, so this is my D, is I need to somehow change the shape of this disk into an upper half plane, upper half space, and then find the heat map H. So actually we found the heat map here. So then we have to composite these functions. So let's say this is F and this H to be H tilde, what we really want. Okay? So the way we have, where we can define F is the following. So let's say this D is lying inside of UV plane. So because I don't want to confuse X and Y here. So F UV is X comma Y. So this is X and this is Y. And the formula for X is 2U, U square, 1 plus V square. And formula for Y is 1 minus U square, V square, divided by U square plus 1 minus V square. So when you do that, then, so I put these 4 points in a symmetric way. So let's call it A, B, C, D. And A goes to -1, and sorry, it's A not going to -1. B is going to -1, and C is going to 0, and D is going to 1. So the boundary condition on the far left is the boundary condition for this part, the C0 here, this C0. And between B and C, you get C1, and between C and D and C2, and after D, you get C3. So I'm not giving you the detail why I could have, where I can have, where did this formula come from, and where, how I can get this boundary condition and corresponding the pieces boundary here, because it requires some materials in the engineering mathematics 2 and the complex numbers. So it actually appears in the second part of engineering mathematics 2. So, but that even without knowing the detailed theory, we can still do all these things, right? Using the partial differential concepts of partial differentials. Anyway, so the strategy is, now we converted the problem of the boundary condition of the disk into the problem of boundary condition of the upper half plane, and we can solve that problem. We already solved it. This is our solution. This is our heat map, right? So then what we'd have to do is take the function by composition of F, this function F, and H. All we have to do next is draw the contour plots of H tilde. Then we get the contour line inside of the disk in a nice way. Okay. You can do more. I'll maybe show you after next time. If you want to change the shape of your boundaries or length of your boundary, you can still change the boundary as long as you know where the points are mapping into the boundary of the upper half plane, right? And you can even increase the number of pieces of your boundary conditions, right? So, and The changing the shape of your disk is different story because you need a kind of background. You need certain conditions. So one condition that I didn't mention is that the F is actually chosen carefully so that it preserves the angle. So this F must be a conformal map. So map that preserves the angle between two vectors. So this function F is chosen carefully so that it satisfies two conditions. One is that it maps every point in D to every point in H, one-to-one fashion. And also it preserves the angle. If any two vectors are intersecting each other and with a certain angle, at every point that angle is preserved. So there's only one thing that does that. And if you want to change the shape D, then you have to find a function that satisfies these two conditions. So it's not easy task, but in hydrodynamics and also in other engineering parts, they are thinking about many formulas that can be used to make a shape of other surface or boundary shapes, so that we can think about boundary conditions and find the function that satisfies the boundary condition. But I just want you to do up to this part, finding the heat map on the disk with given the boundary condition on the disk.